I'm now going to tell you about some applications of the law of total expectation, that very powerful, technique that we can use to simplify expectations. Okay, now, law of total expectation. Okay, now, one reformulation of the law of total expectation leads us to a tool or a concept called iterated expectation. Okay, so iterated expectation. And I'm not going to cover that here. You can read all about it in the text. Okay, so see text. Okay. What I'm going to talk about is the application of the law of total expectation to build up expectation. So, just like we had build-up counting, it's possible to compute expectations by starting small and building up to larger problems. Okay. So, we will showcase this with a very specific example, but just let me remind you what the law of total expectation is. So, you're computing the expected value of a random variable x, okay, and you break it down into two cases, case A and case not A. And, it's kind of a case-by-case analysis. So the expected value of x is the expected value of x conditioned on being in case A, weighted by the probability of being in case A, plus the expected value of x conditioned on being in case not A times weighted by the probability of not A. Okay. So it's not just the sum of conditional expectations. You have to weight by the appropriate probabilities. Okay. Now, we studied the waiting time to K boys, and we studied the waiting time, and that equivalently can be the waiting time to K girls. Okay, so, the waiting time to K boys is equal to, so you're waiting for K successes. Think of a boy as a success, and the probability of success is 1/2. So it's K over 1/2. We derive this, so that's 2K. And the waiting time to K, to let's say L girls. Now think of the girl as the success. The probability of a girl is 1/2. So it's going to equal L over 1/2, L over the probability of success, which is again 2L. No surprise. The waiting time, the expected wait for K boys is twice the number of boys you're waiting for. And the waiting time, the expected number of kids to L girls is twice the number of girls. But now let's add a twist. Supposing you're going to have kids until you have, 3 boys and 3 girls. So the waiting time to 3 boys and 3 girls, okay, is what? So you could have boy, 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 then girl, 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 and that now you could have more than 3 boys, okay, but you're still waiting because you're also waiting for 3 girls. Okay, this is more complicated. It's actually a lot more complicated, but we can solve it with the build-up method. Okay, and the general idea when you're using the build-up method is you start, from some more complex problem and try to reduce it to a simpler problem. And when you're analyzing this reduction, this recursion, so to speak, it helps to sort of consider the general case of a bigger problem and try to reduce it to an instance of the smaller problem. So let us consider the waiting time to K boys and L girls. So the most general version of this problem. Here you're waiting for K boys, only boys. Here you're only interested in girls, so you're waiting for L girls. Okay. Here it's specific, 3 boys and 3 girls. But look at the general problem. Waiting for K boys and K girls. Okay. And it's useful to give this a notation. Let's call this the waiting time W for K boys and L girls. Okay. So it's always useful when you're doing build-up to have a notation for the thing you're trying to compute, and then we're going to try to now relate this to smaller values of K and L. So for example, let's start with some easy cases. You're waiting for K boys and 0 girls. Well, we just computed that. That's waiting for K boys. Okay, so that's 2K. You're waiting for 0 boys and L girls. Well, we computed that. The waiting time to L girls. That's 2L. Now let's see if we can analyze in general. So remember, this is the expected waiting time. Sorry, I should say the expected. And in all cases, it's the expected. It's the expected. It's the expected. So we're talking about expected values. Okay. So what is the expected waiting time, to K boys and K girls? So the expected waiting time for K boys and L girls. Now we just use the law of total expectation. It says it's the expected weight, the expected value of the weight, given that the first child is a boy. So case 1, case A, the first child is a boy, times the probability that the first child is a boy, plus the expected weight given that the first child is not a boy, i.e. a girl, times the probability that the first child is a girl. Okay? Well, let's see. What's the okay, so this is a half. 1/2. This is a half. 1/2. Okay? What is the expected weight given that the first child is a boy? Okay, well, you've had one child, which is the boy, so you have one child. Okay? And now you're waiting for what? You started waiting for K boys and L girls. You've had one boy, so that's one child, plus you're going to be waiting for K minus 1 boys and L girls, because you've had a boy. So this is going to be 1 plus W of K minus 1 and L. The expected waiting time to K minus 1 boys, because you've had a boy, and L girls, because you were originally waiting for L girls. Okay? And this guy here is 1 plus the waiting time to the K boys you were originally waiting for, but you had a girl. So that's this 1. Okay? Now you're waiting for K boys and L minus 1 girls. Okay, and this guy here is exactly W of K and L. Okay, so what have we proved? W of K and L is equal to 1 plus W K minus 1 L times a half plus 1 plus W K L minus 1 times a half, which is equal to, so W of K and L is equal to 1 times a half plus 1 times a half is 1 plus 1/2 W of K minus 1 L plus 1/2 W of K L minus 1. Bam! That's it. There's our build-up recursion. It tells us how to compute the expected waiting time to K boys and L girls. It doesn't actually tell us how to compute it. It just says it's related to smaller problems. Waiting for K minus 1 boys and L girls, or waiting for K boys and L minus 1 girls. Okay. So let's see how we can use this to compute the expected weight to 3 boys and 3 girls. Okay. So let me put K here. That's the number of boys you're waiting for, and L here. So you could be waiting for 0 boys, 1 boy, 2, 3, and so on. You could be waiting for 0 girls, 1 girl, 2 girls, 3 girls, 4 girls, and so on. If you're waiting for 0 boys, okay, so the waiting time for 0 boys and any number of girls is just twice the number of girls. So you don't have to wait at all if you're interested in no kids. You're done. Okay? If you're waiting for 1 girl and 0 boys, you wait on average 2 kids. On average 4 kids. On average 6 kids, 8, and so on. Okay. On the other hand, if it's 0 girls and you're waiting for K boys, on average, if it's 1 boy, 2 kids. 2 boys, 4 kids. 3 boys, 6 kids. Okay. Now, let's see what this is saying. What this recursion says is, let's say we're interested in 2 boys and 1 girl. It says, you take 1, okay, and you're going to take the average, so 1/2 of this sum. What is this sum? That's 1/2 of, it's the average of these 2. Okay, this is K minus 1, so you go up in K. So you go up in K, and you go L minus 1, so you go left in L. So you go left in L. You take the average and add 1. So this is going to be 3. Take the average and add 1. So the average of these is 3.5. So you add 1, 4.5. Take the average and add 1, 5.25. 0.25. Okay, so this is going to be, take the average and add 1. So 5.25, 6.25. Okay. Take the average and add 1. So 3.5, 4.5. Okay. Take the average and add 1. So 5.5. Okay. Take the average and add 1. So here we're going to have 6.25. Okay, and we're getting there. Okay, now take the average and add 1. So this is 8.875. Sorry, 6.875. Okay, and the same thing here, 6.875. Take the average and add 1, so 7.875. Bam! Look at that! Such an odd number of children. Okay, I'm just using this recursion to build up, to fill in this table. Okay, and what we observe is that when you grow up and you get married and you're deciding to have kids, and if you're waiting and you'll continue to have kids until you have 3 boys and 3 girls. I don't know who's going to do that, but let's say you do. You're expecting to have a little under 8 kids to get 3 boys and 3 girls. So let's say 8 kids. So I expect to have 8 kids. Okay. So that's an example of the build-up method for computing expectations. Now, I want to tell you about indicator random variables. And when used with this theorem on the expected value of a sum is the sum of expected values, very powerful, very surprising, very stunning results can pop up.